In this video, I'll be talking about probabilistic quadrature rules, which are essentially ways to compute integrals using probabilistic methods. First, I'll provide a survey of some Monte Carlo methods, and then I hope to convince you why Bayes' theorem has anything to do with computing integrals. So first of all, suppose you want to compute an integral of this kind, where you're integrating f against a density function mu. For example, you could have this integral right here where you're integrating x squared on the interval 0, 1. And you can understand it as f being x squared and then mu here being the characteristic function. So if you put a 1 there, this becomes the density function of the uniform random variable on 0, 1. The merit of this approach is that it allows you to understand this integral as the expectation of a function of a random variable. So presumably, you could sample n points independently from this random variable, and their mean would give you an approximation of the mean of the random variable that you want, which is in turn the integral that you want to compute. This approach is in general termed Monte Carlo integration. So for example, um, you can have um, x squared being the function and mu x as the characteristic function being the underlying random variable. And you can generalize this approach to any domain that you're integrating on to integrate any function that you want. So for example, you may have um, you can set mu to be the characteristic function divided by the volume to make it a density function, and you can multiply the integrand by the right characteristic function to turn this into a Monte Carlo problem, because this right here is in the f times mu form. This approach is called simple Monte Carlo. Um, and let's use simple Monte Carlo to find the volume of the three-dimensional L1 unit ball. So what is the three-dimensional L1 unit ball? It's this octahedron right here. From trigonometry, we know that its volume is 4/3, but let's find that using integration. So first of all, we can write down the volume as an integral by integrating 1 on the octahedron, and then we just uh, convert the integral into a product of characteristic functions on the unit cube. And we just sample n points uniformly in the unit cube in 3 dimensions, and then if those points lie in the octahedron, we record a 1. If not, we record a 0. And then we add up all the ones, divide by n, and then multiply by 8 to get our estimate. So I've computed a few values here for you, and we see that indeed for like a million samples, the Monte Carlo estimate is like pretty close to the actual answer. But when we're using like say 100 points, we don't even get within 1 digit or 2 digits of accuracy. And this is because the variance of the estimator that we found earlier can actually be given via the variance of the underlying distribution, which we chose to be uniform. And presumably, if we tweak the underlying distribution on X, we could potentially decrease the variance that we had on our estimator. This approach is termed importance sampling, and we'll demonstrate it through this example right here. So suppose we're trying to integrate 2 times 1 minus x times e to the x on the interval 0 to 1. In the simple Monte Carlo scheme, we just pick f to be this function and mu to be the characteristic function. On the other hand, in the importance sampling scheme, we pick f to be just the exponential and then the density function to be this 2 times 1 minus x term. So we'll be sampling points in the interval 0 to 1 with density 2 times 1 minus x. And this approach actually does decrease our variance, but we see that it decreases it by a constant, and it doesn't help the rate of convergence of of the variance of our estimator. And to fix this problem, we use another algorithm called recursive stratified sampling, and it works this way. Um, we take our domain and then we divide it into two halves of equal volume, and then we compute the integral here, compute the integral there, and then take the average of the two integrals we found. And you can understand this as a special case of the Monte Carlo estimator, because we basically sample half the points from one half, and then the other half of the points come from the other half of the domain, instead of them all coming randomly from anywhere, in which is the case in simple Monte Carlo. And why do we do this is because the parallel axis theorem says that this way of computing the integral actually improves our variance than if we did it just using simple Monte Carlo. Um, and that gives us an algorithm because we can just keep subdividing our domain this way. We divide it into halves, and then we divide A and B into halves each, and go on, and so on, and then keep computing integral on each partition. And so we see that recursive stratified sampling does indeed decrease our um, does indeed increase our rate of convergence from half to, say, something a little bit more than half on the standard deviation. Um, so just to summarize the Monte Carlo methods, they all sort of implement the Monte Carlo estimator in different ways. Simple Monte Carlo just uses the uniform distribution, importance sampling. By changing the distribution to something that's non-uniform, maintains the rate of convergence but improves the variance by a constant. On the other hand, the RSS algorithm works by subdividing the domain. So when the function is cheap to sample, you should use RSS because in the long run, your convergence is better using the subdivisions. But at the same time, um, these methods are still pretty inaccurate because we still would need about 1 million samples to get to even within 4 digits of the answer that we want. And at this point, the Bayes' theorem makes a grand entrance to dramatically solve this problem. So what is the Bayes approach and how do we do it? So first of all, the Bayesian strategy is to observe that I depends on the values of f that you see. And there is no way to even know the values of f unless you actually sample it. So there is inherently an uncertainty in the value of f. And you should and we use our samples to sharpen our beliefs about what f is. So presumably if we have a prior on f, the sample, we can condition on the samples to get a posterior on f, um, and you can compute the integral on the posterior distribution as a result, um, and get something. And this is the content of the Bayesian quadrature approach. So once we condition on the sample, we can compute the integral on the posterior distribution to estimate our integral. And so the natural question arises, what should be a prior for our function? And one obvious approach is to say that, well, at any point, the function value is normally distributed, which is the approach we took in Bayesian linear regression. So for example, here's a prior of the function. We say that on average, yes, the function looks like this blue line right here, but 90% of the time, the values of the function would lie in this light blue region over here. Um, so um, this model is called, this model can be formalized in terms of, and could be called a Gaussian process. And a Gaussian process is a distribution on functions where any finite collection of points is distributed um, in a joint normal distribution, and the covariance matrix satisfies certain properties of symmetry, positivity, and one definiteness. Um, what does this mean? It means essentially that if f is distributed in a Gaussian process, then Any sample of points from F is jointly normally distributed, and because of the properties of the covariance function, the closer the points are, the more correlated the values of F are. So, for example, if you just pick one point, then F is at that point is distributed normally, um, which is the intuition we had um, um, from, say, the linear regression point of view. Um, and so, for example, here's like a function from sampled from here's 5 functions sampled from a Gaussian process. Essentially, we pick 41 points in the domain, and then we sample from a 41 dimensional joint normal distribution. And to answer our original question about how to compute our integrals, we take the help of the following results. First of all, the first result that we want is to say that that the Gaussian process model is essentially a conjugate prior likelihood model, because um, conditioning on a Gaussian process gets you back on a set of samples gets you back a Gaussian process as a posterior. And as a corollary, we have a closed form for the mean of the Gaussian process at a given point. Um, Additionally, we have the theorem that says that expectations will commute. So if you want to find um, on average the value of functions over the Gaussian process of the integral here is the same as if you integrated the posterior mean um, on the random variable x. And what does this mean? Essentially, it means that we use our samples to sharpen our beliefs about what f is. So now we know that f always lives somewhere in this red region. And the third theorem basically says that a good approximation for the integral of f is just the integral of this mean function that you see right here. And incidentally, we actually have a closed formula for the mean of the random variable. And so we can just plug this into the integral formulation to get an estimate of the integral that we want. And presumably, if you're able to compute this vector here analytically, then you should be able to compute this estimator with no problem. So we implement Bayesian quadrature on the original function that we started with. And so the first thing to do is to actually define what this function, the covariance function k should be. So first of all, it should satisfy these three properties of symmetry, positivity, and non-definiteness. And to do that, I picked the Lorentzian kernel, which is essentially this function. And the convenient thing about this function is that its integral, when integrated against just the one function, is analytical. So you can compute it, you can express it in arctangent. And so it's really easy to compute this vector right here. And so once we put these pieces together, we can compute the integral that we want using Bayesian quadrature, and the results are pretty stunning. We see that the Bayesian algorithm gets within 4 digits of accuracy in only in 10 samples, while Monte Carlo we know might take many more than just 1,000 samples. But at the same time, Bayesian quadrature is kind of numerically unstable, because to compute the estimator, we actually have to invert a large matrix, and that's not easy. And it's a very poorly conditioned problem. So in conclusion, Monte Carlo methods are good because they're numerically really efficient, and they don't depend on the dimension of the integrals. You can compute really high dimensional integrals. At the same time, they're on the whole quite inaccurate, and so we use importance sampling and the RSS algorithms to improve our convergence the variance properties of the Monte Carlo estimator. But it seems that none of them are quite as accurate as Bayesian quadrature. But at the same time, Bayesian quadrature suffers from dimensionality issues and conditioning issues because we have to invert a large matrix. So that kind of leads us to the conclusion that there is no real one size fits all approach to quadrature, and you really have to pick your method based on the problem that you have. But I hope in this video I've convinced you why Bayesian quadrature and the Bayesian sort of thinking is pretty relevant even in a seemingly unrelated problem like computing integrals. And I'll be happy to take any questions by email since I seem to not be here live. Um, Thank you.